level of signal processing. So we don't just know the statement, the result, but we want to know what's the reason behind. And we have to rigorously prove it. You know, you have a wire systems, you have to prove that the system works all the time, right? And you know, some mathematical term you have to prove the statement. So that is important, and people out there design those systems, they really understand the thing very deeply in that level. Okay. And in the homework exercise, you will have a chance to review those steps. Okay. So I'm going to prove this theorem here, and to me it's a very fundamental theorem. It's not just in signal processing, but in general linear systems theory. Okay. And in the process of proving these theorems, we will touch upon the following concept of signal decompositions, right? Signal decompositions. But let me ask first, who has seen this theorem before? Raise your hand. Okay, a few of them. Who has seen to prove this theorem before? One. Who can prove this theorem? Okay. So it's worth to go through the proof, right? Okay. So, you know, you have to have a proof of this theory. And that's why I wouldn't say, you know, we want to understand the thing deeply, and we keep ourselves all with questions where this result comes from, right? One of the things that key inside my web research is I never stop questioning, right? Always ask questions. And that is what when we see this thing. So okay, I have to do this proof. Okay. First, let me notice this whole thing. Notice I have a signal X. Signal Xn is a synchronous sample like this. And I have n here. So this is signal, right? Oh, by the way, I use the notation n with the square around it. You know that it is a discrete signal. The n here is an integer. Okay, so it's a sequence here, so we have here's a value n, 0, 1, 2, and each n here I have a value. So signal is the whole sequence. Okay? So I have that signal, and I thought very hard to deal with the signal, like the whole sequence. And here we can use a strategy that the Romans used 2,000 years ago when they want to conquer the world. What they want to do is divide and conquer. Right? I break the signal into small pieces, and I deal with each piece separately. Right? You have big problems. The way to solve it is break it into small tasks, and you deal with them separately. So that is one techniques that an engineer or a DSP engineer have to master. Okay, so I have a signal here, and I want to break it into small pieces. Small pieces. And one way to do that is maybe I have a signal, I can think about the simplest summation of a signal that first only have this, and a signal only have that, a signal only have this, and so on. Right? So if I just add them all together, I have the original signal. Can you see that? So I can notice that Xn here is equal to summations. Rather the more complicated way is I write them in the xk delta of n minus k. Okay, so the delta n minus k here, if you think about that, delta of n is a signal here. N minus k, you just relate it by k. And you have one here. And you take that and you weigh them by hk. Okay? So this thing you can verify, right? But it's really stable to break the signal into small pieces. Now that value is, I want to agree with this, right? Now I want to write them in my operation here. I want to treat this equation a little bit differently. Either here is the signal, and I want to put them in the square bracket. And this simple summation here, I put this square bracket here is a signal, and this is a scale, a number. Okay. Everyone understand the difference between a number and a signal now, right? A signal is like a function or sequence. So you have a value at every instant of time or instant of or every time. A number is just one number. Okay? So here I have a signal here, it is representing its annual value for every n. And this equation here, so now it is one simple signal weighted by this. Okay, so now you see more clearly the thing can break this signal into summaries of those small signals. Alright, let's say one. So I have a graph now. So now if I apply the first linear property, the L here is I allow it to turn S, apply on its end, and the linear property tell me that simply equal to the summation of xk. So these are just weight. Those are just weight. Okay, those weight here. And I put the S and I see what is output like delta. Okay, so type that S and delta n minus k. Alright, moving, right? That is the linear property put in place. Now, I'm using the TI now. The TI property tell me now. If I have only n here, what is that to do? Hn by my definitions. Now I have this property Hn minus k because the system is a time variable. So using the time variable now, I can replace this thing now by Hn minus k. That's it. That's what I get my theorem, right? Exactly the formula showing there. Okay. So a very simple two-line proof, but it carry the very important concept I want to reinforce later is I prove the signal based on breaking the signal into small manageable pieces. Okay? And understand where is a value and where is a signal. Okay? So if you haven't catch up this, tonight exercise, try to repeat it. Very important theorem. Where the statement and how to prove it. Okay. And as I tell you, it has extremely important impact in signal processing and many other areas, right? For example, one of the areas very hot now, I know, is the bioengineering, right? So people study a particular cell, a neuron cell, for example, right? So that cell we have modeled because the cell, including some input, you get send some signal, right? Our whole body is just a sequential system, right? This, you have something, let's say the temperature, the cell reacts something, and it transmits something, and it send the neural signal all the way back to the brain, right? And people try to understand that very complicated systems. And what they do is they break into small pieces, and for each system, one way to understand the system is they send some inputs, something like delta here. They record the output. And then they can know exactly what the system is doing. Try to model the system. People want to understand what is communication from here to Mars, for example. And this channel is very hard. All you have to do is send the input and let the other side record it. And then you know what is a communication channel for the whole system. Right? So those are important. So, in that particular proof, I want to carry on now another concept of breaking things into small pieces. The theorem is showing this convolution and its result, the name, and you see later. So this operation is happening all the time, and this thing here now I can write this H convoluted H, and I have n. So you know that H is a whole signal, H is another signal. I convert two things, right, using this formula. I got something for every instant of time. Okay. So the signal I have so far, I think about them as a function or a sequence of numbers. Now, another way to think about the signal now, rather modern concept, which will be used later on, is now to think about the signal